It's time to use all those wonderful correlations to not just describe things, but to now start predicting things. Let's get into it. We are going to talk about predictions, this thing called the line of best fit, the regression line equation, and we're going to do some examples with multiple regression and some regression in R. Regression and prediction. If we think back to the beginning of this class, we know that the only way that we can establish causation is with a true experiment and in some cases a quasi-experiment. Now that we are just using correlations, we can't, of course, establish causation, but we can use the correlations to help us make predictions. So if you studied X number of hours, you most likely get Y number of questions correct. So I'm going to use this number of hours to predict the questions that you will get correct. Would higher or lower correlation values, this R, result in more accurate predictions? Do we want the correlation to be high or do we want the correlation to be low? Ideally, we want that correlation to be high, so it is more predictive. So if you know how many hours one person studied, you can try to predict how many questions they will answer correctly. Let's look back at our old example where we have this line for the correlation and we have hours studied on the x-axis and the number of questions correct on the y-axis. If someone were to have studied for 3 hours, how many questions would you predict that they get right? Well, you can look here at 3. If we go straight up and we're going to follow this line, we go all the way across, we see that they would get about 6 right. That's what we would predict based on our information. So regression analysis is used to measure the linear association between quantitative variables. Correlation describes the strength of a relationship between two variables, while a regression is used to predict values for our response variable y, the number of questions you get correct, based on the explanatory variable, the number of hours that you studied. And that line that we are looking at is called the line of best fit, and it is our best guess at predicting one variable from another. How does this line of best fit come to be? Well, it is a regression statistic that attempts to find a line that crosses through as many data points as possible while minimizing the distance from those points. So here are a bunch of data points. Each one of these is a person and their score on X and their score on Y. And we are trying to put a line in between them, the best line that we can find that is going to minimize all this space between the line and the points. Now our goal is to fit a line that minimizes the distance from the points and that line. But, as you might have guessed, the observed values in our data will usually be a little bit different from the predicted values from that regression line. The difference between our observed value and the predicted values from the regression line are called residuals. What are residuals? It's the observed value, so if you had a score of 10, but it was predicted that you would get a score of 9, there is 1 point that's a residual. It's basically how off you were. Would we want our residuals to be as small as possible or as big as possible? Are residuals a good thing or a bad thing? We want the residuals to be as small as possible, and we do this with a technique called ordinary least squares that is beyond the scope of this class, but it's really interesting. I recommend that if you take any higher level maths or statistics, learn some of that good stuff. So we have, again, our observed score, which is the score that you actually got. We have a predicted score based on how many hours you studied. We're going to try to predict your score, and then we'll have the residuals, which is how off I might have been with my prediction from the truth, your actual observed score. Regression line equation. Now let's investigate this equation. Here we have our x value, which is the observed value of the number of hours that you studied, and this is what we are going to use to explain your grade. This is our explanatory variable. Now we have this beta 1, and this is basically the slope if you're thinking about this old equation from math class. This is how much your predicted score is going to go up for every increment of x. So if you study 1 additional hour, how many more questions are you going to get correct? Then our beta naught, or beta sub 0, whatever you'd like to call it, it's also the y-intercept. This is your score if you did not study at all, basically. If this part of the equation was gone, so if you studied 0 hours, this would be 0. This would be your score if you had an x value of 0. So this, again, is the y-intercept. It's where the line crosses the y-axis. And then we have our y-hat, which is the predicted value. This is what we are predicting based on the number of hours you studied. This is how many questions we expect you to get correct. So let's look at an example. We're trying to predict house prices. Now this is totally not accurate for Austin because it's ridiculously expensive here, but let's just use it anyway. So first off, What is the explanatory variable and what is the response variable? Be trying to answer all of these. What would be the predicted price of a home that is 0 square feet? Is it a home then, or just a lot? What would be the predicted price of a home that was 2,000 square feet? If this house is 2,000 square feet and it actually sold for $160,000, did our regression line over or underestimate the selling price? What would be the residual? Take a moment to try to answer some of these, pause me, and then we'll go through them. Let's have a look. So, what is the explanatory variable? We are going to try to explain the price of a house by its size. So the explanatory variable, that x variable here, is the size of the house in square feet. And what is the response variable, or the thing we're trying to predict? That is the price of the house, our price hat. Now, what is the predicted price of a home that is 0 square feet? It is going to be $9,161, because if it was 0 square feet, you'd put a 0 here times 77, and all this would go away, and you're just left with the intercept. So if a house could increase its size by 1 square foot, how much would we expect the selling price of the home to change? So if you increment this by 1, you add another square foot, how much is the price going to go up? 77, because that is that slope. For every unit increase in square foot, y goes up by 77. That house actually sold for $160,000. Did our regression line over or underestimate? We overestimated ever so slightly. But what would the residuals be? We take the observed minus the predicted, and we end up with $3,161 that we were overestimating. Now, as you can see, regression lines, for the most part, are always going to be a little bit off. But by fitting that good line, we can get closer and closer to making predictions. Our other best guess would just be to predict the average for something. That's usually what is being compared against when you're doing a regression line versus basically just the average. And if your regression line is better than the average, hooray! So how do we actually go about finding these values, these coefficients? Well, we would use a computer usually, but let's walk through an example of how we actually get to these values. So this beta 1 is actually going to be the standard deviation of y, the response variable, over the standard deviation of x, the explanatory variable, times their correlation, the correlation between x and y. And that gives us the beta 1, the slope. Now how do we get the intercept? Well, we take the average of the response variable, so in this case, what was the average number of questions that students got correct? And we subtract the beta 1, so this coefficient up here that we did, times the average of the explanatory variable, so the number of hours that people studied. So let's actually walk through a full example. Here we have the same example we've been working with the number of hours you study and the number of questions you get correct. We have some information here, such as the average of both variables and the standard deviation of both variables and their correlation. So go and find everything. Let's go. So let's go and find the slope, or that beta 1 coefficient. So the first things we need are the standard deviations for y, which is 3.54. That's the standard deviation in the response variable, or the number of questions that people are answering correctly. Then we have the standard deviation for the number of hours that people were studying, 1.92. We multiply that by the correlation between x and y, which was 0.96. And we end up with about 1.77. So how do we interpret this? Basically, it means that for every additional hour that you study, you are predicted to get another 1.77 questions correct. Now let's go and find the intercept. We can take the average of y, which was 6, and we're going to subtract that beta 1 that we just found, the slope, times the average of x, and we end up with 1.044. Now what does this mean? This means that if you didn't study at all, which you should, you are predicted to get at least 1 question correct. So here's our full regression equation. Again, reiterating, the number of questions you get correct is based on this intercept, which if you didn't study at all, you'd get at least 1 question right, plus the number of hours you studied times this slope coefficient of 1.77. And that is how we can predict your score. Now that we have our regression equation for the number of hours you spend studying and the number of questions you get correct, let's make some predictions. Pause me for a moment and try to figure out what would your predicted y hat score, the number of questions you get correct, what would that score be if you studied 4 hours, 6 hours, and 0 hours? Pause me and give it a go. Well, if you go and fill all that in, you end up with If you studied for 4 hours, 4 times 1.77 plus 1.044 is about 8 questions correct. If you studied for 6 hours, you'll get about 11.5 questions correct. And if you don't study at all, this whole term drops out and you end up with about 1 question correct. So study. Multiple regression. Simple linear regression using one predictor variable is all well and good, but rarely are the outcomes of interest explained by just one variable. Life is complicated. There are a lot of things that go into things. With multiple regression, we can add in more than one explanatory variable to try to predict a certain response outcome. The examples for multiple regression are endless, so here are just a few. What variables predict the number of asthma-related emergency department visits for a county? This is actually research I'm doing right now, and we are trying to predict asthma-related ED, emergency department visits, based on different variables. What kind of variables do you think would explain why somebody not just has asthma, but has to go to the emergency department? What sorts of factors might increase the chances of you having to go to the emergency department? Well, you might think certain allergens maybe, or maybe if your asthma is not well controlled. So maybe if you are maybe impoverished and you don't have access to health care, there are a lot of different factors that can go into it. So if you can think of any good ones, let me know. We'll see if we can add it into my regression equations. What about what variables predict the risk of a person having a heart attack in the next year? There are a lot of different things there, like smoking, age, weight, gender, a long list. People are constantly trying to figure this out. And how about what variables predict your level of happiness? I mean, maybe income to some extent, maybe your satisfaction in your job. I mean, what else do you think might go into your level of happiness? What outcomes would you like to run a multiple regression on? Imagine that you had all the data. You had a big data set of everything that you were really interested in, which is rarely the case. But let's think big here. What kind of outcome would you want to run a regression on? What would you be trying to predict? And what variables do you think would be important in making that prediction? Think about this for a while. It's fun to think about these kind of things. So here is our house example again, but now we've added in bedrooms as another predictor. So now we have size and bedrooms that are going to try to predict the price. Beta 1 is still the intercept. It's the price of the house if there was 0 square foot and 0 bedrooms now. And beta 1 now is how much the price is expected to go up for every additional increment of size, so square feet, holding the bedroom one constant. So you have to hold any other variables constant so you can predict the effect of just this one. Now the beta 2 is how much the price is expected to go up for every additional bedroom, holding size constant. Here is a made-up example, so don't use this as your metric to try to get into grad school, though some of it is important. Suppose the regression line equation here predicts the chances of getting into graduate school from the following variables. We have GPA in the 4-point scale, research experience in the number of years, the number of publications you have, and your GRE score in the GRE format. So here is our entire regression line, and the intercept I'm going to say is 0, because if you don't have any of these things, I don't think you could get into grad school. Maybe. I don't know, maybe. Maybe those like exceptional savant kids. Anyway, so here are all of our beta coefficients, and again, these are made up, but I'm going to say that a GPA, for every additional point of GPA, your predicted admission score will go up by 3 points. For every additional year of research experience you have, your score will go up by 4.5 points. For every publication you have, your score will go up by 8 points, and your GRE score is just worth your GRE score. So we already know that the explanatory variables are GPA, research experience, publications, and your GRE, and the outcome variable is your score to get into grad school. Again, I made this up for the sake of an example. So what is the predicted admission score if an applicant had no publications, no research experience, no GRE score, and a GPA of 2.0? And then go and compute the scores for this person, scenario number 1 and scenario number 2. Pause me. Do this. Give it a go. All right. If a person had a GPA of 2.0 and nothing else, their predicted admission score would be 6. Really tiny. Now, how about these two people? So for a person who has a GPA of 3.5, 1.5 years of research experience, 1 publication, and a GRE score of 160, you put all that into our equation here, and this person has a predicted score of 185.25. Now, for scenario number 2, we have a person who has a higher GPA, 3.8, less research experience, 0.5, no publications, but a higher GRE score. Now, if you were to just look at this, you might think that, well, this candidate looks pretty good, but things like research experience and publications, and this is true, are weighted very heavily in graduate school, probably more than I've given them weight here. So if we were to run this one and predict this person's score, they're actually a little bit lower, 180. Even though they did better on GRE, even though they had a better GPA, research experience and publications had a stronger effect, and this person ended up with the higher score. So here is another regression example, but I want you to go and make one up, and if you want to share it with me, you're more than welcome. I would love to see them. But how about you make a regression line for how attractive you are to someone, or maybe how much partner potential somebody has. So there are a bunch of different things that, will dictate how attracted we are to a person, right? Like intelligence, physical appearance, humor, athleticism, are they spiritual? There's a lot more to add, of course, to this list. It's not exhaustive. But the point is, just like in our graduate admissions example, that certain things are going to weigh more heavily than others and kind of compensate. So maybe somebody is not as physically attractive as you'd like them to be, but they are wicked smart and hilarious. And now they're super attractive to you. And there might be some things that are complete non-starters, like if they are not intelligent at all, like their score is just, doesn't matter how attractive they are, how funny. If they're not intelligent, their score is still going to be kind of low. So create one for yourself. Like, how much do you think intelligence is worth to you? How much do you think physical attractiveness is important to you? Give it a go. Of course, if you were going to do this in real life, you'd have to run some numbers and do some actual equating, but this is just, again, to give you an idea of what regression lines and equations can actually do, and multiple regression is just fabulous. I love it. So give it a go. Let's see what you come up with. Let's see what's important to you. For the very last topic of this course, we will finally switch gears. The statistical tests we've looked at so far have been using quantitative data. For our last few topics, we are going to look at some categorical data. So we will be looking at contingency tables and chi-squared tests. I will see you there. Regression in R. Now, in actual statistical practice, you would never calculate any of this by hand because it would take you forever. Can you imagine doing a multiple regression with thousands of data points? So let's actually play with R a little bit because this is way more fun. And I highly encourage you to go out there and find some data sets. There are just countless of them out there, and you can just run this really quickly. It's really fun. Let's go. I'm going to try to convince you. Okay, back to our studying and the number of answers you get correct. First, I'm telling R the data. These are the hours. Here are the questions. I can go and get that correlation again, and it'll be 0.96. I just say core, number of hours, and questions. Now, if I want to run that regression, this is a simple regression because we only have one predictor here, the hours. So we're going to call this the regression model, and I'm going to name it with that little arrow and everything. Now I'm going to just call this function called LM. So easy, right? LM, parentheses, we have questions, tilde, hours. So what's going on here? I'm saying predict the number of questions answered correctly using hours. Now, if you run that, you will have this regression model. Then to actually look at the results, you type summary and put that regression model that you just made here in there. Now here is the output. Now I know at first it's a little bit intimidating, but once you get the hang of this, it makes your life so much easier and more interesting. Okay, so the first thing that we can look at here, we have the intercept, right? Our beta naught, so it's the number of questions you would get correct if you did not study at all, if you had 0 number of hours studying. And it's that 1.0 something. It's a little bit different from our hand calculations because we did them by hand and we can't get as far out and as precise. Now we have the coefficient, the beta 1 that we're interested in. Here we are. And this is that slope. This is again how much your score is predicted to increase if you were to study another hour. And we have 1.76. Again, it's going to be a little bit rounded differently because in our example above, we did it by hand. And then we have our standard error and some t-values associated with all this. This is important, but for now, just look right here. We can still get a p-value for this, basically saying, is the number of hours actually important and predictive and relevant to predicting the number of questions you get correct? Now, our p-value is 0.01111, and we have this little asterisk right here, and that lets you know there's like a little guide here. One asterisk lets you know that it's significant at the 0.05 level, so awesome, super cool. Then we also have this r squared here. Remember r squared? That is the percent of variance that is accounted for by the explanatory variable. So there's our R squared. You don't have to go even calculate that. Go R. Now we have the coefficient, the beta 1 that we're interested in. Here we are. And this is that slope. This is again how much your score is predicted to increase if you were to study another hour. And we have 1.76. Again, it's going to be a little bit rounded differently because in our example above, we did it by hand. And then we have our standard error and some t-values associated with all this. This is important, but for now, just look right here. We can still get a p-value for this, basically saying, is the number of hours actually important and predictive and relevant to predicting the number of questions you get correct? Now, our p-value is 0.01111, and we have this little asterisk right here, and that lets you know there's like a little guide here. One asterisk lets you know that it's significant at the 0.05 level. So awesome, super cool. Then we also have this R squared here. Remember R squared? That is the percent of variance that is accounted for by the explanatory variable. So there's our R squared. You don't have to go even calculate that. Go R. Now here's some good stuff. Not that the other stuff wasn't good stuff. It's just that we only had one predictor and only like 5 data points. Let's get into something a little bit more real. So here we are going to look at a real data set of 500 Indian students trying to apply to graduate school. We are going to run a regression to try to determine what increases your chances of getting into grad school. Now take a moment. Here are all the different explanatory variables we have, and here's our outcome variable. It's the chance of admittance and a 0 to 1 scale. Then we have GRE score, TOEFL score, university ranking, or like the rating of the school, statement of purpose, letters of recommendation, GPA on a 10-point scale instead of the regular 4-point scale that we're used to, and whether they had research or not, just a yes or a no. So out of all these variables, what variables do you think are going to be most predictive of somebody getting into grad school? Look at all those. What do you think? Now to actually run a multiple regression, it is nice and easy. We just read in the data, which it's on Canvas. I recommend you try it. We are going to get the names, and that's just going to tell me all the different variables that are in there because I didn't know what I wanted to include in my regression yet. Then I'm going to call LM, and here is the outcome variable that we're interested in, their chance of admission. Then we're going to have this little tilde here, and we have a GRE score. I'm going to put statement of purpose, letters of recommendation, GPA, and research. Those are the ones I'm going to use to try to explain how likely someone is to get into college. And the data is admissions. So I run that, I saved it as an admissions model, and now I'm going to call summary so it can tell me all the important stuff. Bam! Here is all that important stuff. We got lots going on here. So which explanatory variables were first of all significant? And second of all, of those that were significant, which one had the largest effect? Pause me for just a second so you can look at this and kind of acquaint yourself. So we see that all except one of the predictors was significant, and sadly it was the statement of purpose, which I spent a long time writing my statement of purpose. That's a little bit sad. So statement of purpose, not significant. We don't need to look at that one. And all the rest are significant, but of all those that are significant, which one is the most predictive? And it looks like GPA. For every additional point your GPA goes up, your chances of getting in go up by about 0.13. Also, about 81%, looking at our R squared, of the variance of getting into grad school is accounted for by our model with all of these different predictors. So I hope this one example has at least just a little bit convinced you of the awesomeness of regression. It is a huge topic in statistics and math and research and marketing. It's just amazing. It's fabulous. I highly encourage you to go and find some data online, or even more fun, maybe take a bunch of your own data for a few different variables like how many calories you eat in a day, how much you exercise, how much you sleep, how much caffeine you drink, whatever, and maybe how that affects your grades at the end of the semester, or how that affects your happiness measured by some sort of a scale. It's just endless. You can do so much with this, and I hope I've convinced you of that just a little bit. Just a little bit. All right. I'll see you in the next one.